You're listening to Buried by Time, a podcast about stories, people, places, and events that still have something to tell us. Some are well known, others have nearly disappeared. Let's take a closer look. Dear listeners, a small note before we begin. If you've been paying close attention, you may have noticed that Buried by Time sometimes leaves a trail behind. A name, a casual mention, a strange detail, a passing reference. Not every clue announces itself. Some are hidden in plain sight. Others are fittingly buried. So as you listen, keep one ear open. Somewhere in each episode, there may be a clue pointing towards the next story waiting underneath. Now on to our episode. CERN, buried by timelines. The Large Hadron Collider is a 16.8-mile particle accelerator buried near Geneva, crossing underneath the border between Switzerland and France. It uses powerful superconducting magnets to guide beams of protons around a circular tunnel and bring them into collision inside large instruments called detectors, which are massive, highly sensitive machines designed to observe and record what happens when particles collide. These detectors track the paths, energy, and types of particles produced in the collisions, allowing scientists to reconstruct the event and study the fundamental components of matter. The machine is not hidden and CERN is not secret, but the scale and purpose of the project still make it easy to understand why people question it or feel there is a sense of mystery surrounding it. It is an underground machine built to smash particles and study the unknown structures and makeup of matter. In 2026, the Large Hadron Collider went quiet for a planned upgrade period called Long Shutdown 3. CERN is using this shutdown to prepare the accelerator for its next stage, the High Luminosity Large Hadron Collider, which is expected to produce many more particle collisions and collect much larger amounts of data when it begins operating around 2030. In official terms, this is maintenance and improvement. In the mythology that has grown around CERN, however, the shutdown raises a stranger question. If the collider has been affecting the structure of reality in some unknown way, would turning it off reduce the effect, increase the effect, or allow previous effects to settle into place? There is no scientific proof that CERN has shifted timelines, opened a portal, or caused the Mandela Effect, a term used to describe a phenomenon where large groups of people remember an event, detail, or piece of information differently from how it is recorded in history or reality. CERN's safety arguments are based partly on the fact that nature already produces extremely high-energy particle collisions through cosmic rays, and those collisions have been happening throughout the universe for billions of years. If particle collisions could alone tear apart reality, the universe would already show evidence of that. But the most interesting version of the CERN timeline theory does not depend on the collider acting like a bomb. It depends on a more subtle idea that the machine might not be breaking reality by force, but instead constantly observing and recording tiny quantum events where many possible outcomes exist until a measurement is made and one specific result is fixed and stored as what actually happened. That is the version worth looking at with closer scrutiny, not because it is proven, but because it gives the story a stronger internal logic. In this version, CERN does not create alternate timelines. Instead, it acts as a pressure point where measurement, probability, and information meet. The collider produces huge numbers of subatomic events, and each event is captured by detectors that record what happened. If reality has more than one possible path at the quantum level, then the speculative question becomes whether enough repeated measurement could disturb, select, stabilize, or briefly expose the borders between nearby possibilities. If that kind of effect existed, it would probably not look like a full jump into a completely different world. The changes would be small because the mechanism would be small. People would not wake up to a different planet or a different sky. They would notice details that sit at the edge of memory, a logo that feels wrong, A movie line that seems to have changed, a celebrity death that some people remember happening years earlier, or a song lyric that does not match what they were sure they heard. These would not be giant ruptures in reality, they would be fragments, small pieces of what could be called crossover debris. CERN began after World War II, partly in response to a scientific brain drain that had seen many of Europe's leading physicists move to the United States when European countries were rebuilding and looking for ways to cooperate through science. The CERN Convention entered into force in 1954, creating a laboratory for nuclear and particle research. Over time, CERN became one of the major centers of particle physics, with scientists from many countries working together to study matter, forces, particles, and the early conditions of the universe. The goal was not mystical, it was technical and scientific. Build machines precise enough to test questions about the smallest known parts of nature. That history is important because CERN was not created as a mysterious or symbolic figure in online culture. It only took on that role later as people on the internet began using it as a focal point for speculation and conspiracy theories. The real organization was built around cooperation, engineering, mathematics, detectors, and analysis. The mythology came afterward when the public began trying to imagine what it means to have an underground machine that studies invisible fields and particles most people will never see. CERN's day-to-day work is complicated enough that the simplified public version can easily become distorted. When people hear about particle collisions, hidden fields, antimatter, dark matter searches, or the Higgs boson, the facts can start to sound like science fiction even before anyone adds a conspiracy theory. Long before the Large Hadron Collider became the center of these ideas, CERN had already changed the world in another way. In 1989, Tim Berners-Lee, working at CERN, invented the World Wide Web as a way for scientists to share information across different computers and institutions. That was a practical solution to a research problem, but it became the structure of modern online life. This is one of the most important details in the CERN story because the web did not just connect documents. It eventually allowed people to compare what they remember about events, facts, or details with others around the world at a global scale. Before the web, an unclear or unusual memory usually didn't go too far, experienced only by the individual with no one else to compare it to, so it might be dismissed as a kind of déjà vu. Someone might insist that a commercial had a different line, that a product logo had changed, or that a famous person had died earlier than the record showed. A few people might argue about it, and then the subject would be forgotten. After the web, people could search for the same memory, find strangers who remembered it the same way, and build communities around those shared memory glitches. The Mandela Effect became possible as a mass phenomenon, not necessarily because memory changed, but because the internet made memory searchable. The Mandela Effect takes its name from people who believed they remembered Nelson Mandela dying in prison, even though the historical records show that he was released in 1990, became president of South Africa in 1994, and died in 2013. From that example, the idea expanded into hundreds of claims about altered movie quotes, brand names, song lyrics, book titles, maps, celebrities, and pop culture moments. Many of these examples have ordinary explanations. People misquote lines, brands redesign packaging, parodies replace original memories, the mind fills in missing details. Groups of people can remember the same wrong version because they were exposed to the same wrong version through shared media, repetition, and suggestion, which can make those memories feel uncannily real, even as if reality itself is misleading them. Still, some Mandela Effect examples feel stronger to the people who experience them because the memory is not just a fact in their heads. It comes with context. They remember when they were there, who told them, what the phrase sounded like, or how often they repeated it. That emotional certainty is part of why the idea lasts. A person can accept that memory is unreliable and still feel unsettled when a specific memory seems too clear to be wrong. This is where CERN enters the conversation. The Large Hadron Collider first circulated beams on September 10, 2008, and by 2010 it was producing high-energy collisions. On July 4, 2012, CERN announced the discovery of a new particle consistent with the Higgs boson. The Higgs boson is connected to the Higgs field, which is part of the explanation for why fundamental particles acquire mass. For physicists, the discovery was a major confirmation of the Standard Model, which is the main scientific framework that describes the fundamental particles and forces that make up the universe. For the public, it sounded like a machine under the ground had found something hidden in the structure of reality. That does not mean CERN changed reality. It means CERN revealed evidence for a particle connected to a field that already existed in the theory, and in doing so, brought something hidden into observation, which in quantum terms is the kind of interaction that can influence how reality settles into a measurable state. But for people looking for a timeline explanation, the Higgs discovery became a major date. The public heard that CERN had found the so-called God particle, a nickname many physicists dislike, and the myth almost wrote itself. If a machine can detect something tied to mass itself, then people start asking what else the machine might affect. The strongest speculative version of the timeline theory begins with quantum measurement. People often say that particles behave differently when they are observed, but that wording can be misleading. In physics, observation does not usually mean a person looking at something with the naked eye. It means measurement, interaction with a detector, or interaction with the surrounding environment. A quantum system can be described in terms of possible outcomes, and when it interacts with a measuring device or the larger environment, those possibilities become tied to a recorded result. The real physics does not say that a human mind is magically changing the universe by watching it. The important point is that measurement is not nothing. A detector does not simply look at a particle the way a camera looks at a chair. The detector becomes part of the physical interaction. Information is extracted and a result is recorded. As the system interacts with its surroundings, the different possible outcomes stop overlapping and behaving like a single combined state, and instead separate into distinct possibilities that no longer interfere with each other, while the world we experience appears to settle into one stable outcome. The speculative leap is to ask what happens when this process is scaled up inside a machine like the Large Hadron Collider. The collider creates particle collisions, and the detectors record the traces left behind. Each collision becomes an event where reality has to be described in the data. What particles appeared, where did they go, how did they decay, what energy was measured, what pattern was recorded. The machine does not just smash particles, it creates conditions where possible outcomes become documented outcomes again and again. In the strongest version of the CERN timeline theory, the concern is not that each collision has enough force to shove the planet into another universe. That is not the compelling version. The stronger idea is measurement pressure. The collider repeatedly produces and records events at a level where quantum possibilities become fixed in the data. If there were any unknown connection between quantum measurement and larger scale reality, then the Large Hadron Collider could be imagined as a machine that increases that pressure. This would make CERN less like a portal and more like a selector. It would not create alternate realities from nothing. It would interact with possibilities that already exist. If nearby timelines or branches were part of the structure of reality, then repeated measurements might, in the speculative model, strengthen one branch, weaken another, or create small areas of overlap where one version leaves a trace inside another. That trace would not have to be physical in a dramatic way. It could appear as a mismatch between memory and record. This is where the idea of crossover debris becomes useful. Crossover debris would not mean a whole world has arrived inside this one. It would mean a small detail from a nearby version has become attached to memory, culture, or perception. A person remembers a brand logo with a detail that does not exist. A group of people remember a line from a movie that was never said in the exact way they remember it. A song lyric feels different from the official recording. A public figure's death feels as if it happened years earlier. The record says one thing, but memory carries another. A skeptic would say this is exactly how memory works. Human memory is reconstructive, not photographic. People store impressions, not perfect recordings. When memories are repeated, they can be reshaped. When a wrong version becomes popular, it can replace the original in people's minds. That explanation is strong, and it probably explains many Mandela Effect examples, but the speculative believer would say that memory is also the only place where a small timeline overlap might remain visible. If the public record updates with the dominant timeline, then the remaining evidence would be private memory shared by people who somehow carried the other version across. That is why the CERN theory is hard to prove and hard to kill. The evidence is weak by scientific standards because it depends on memory, and memory is unreliable. At the same time, the emotional force of the memories keeps the theory alive. People do not feel as if they're guessing. They feel as if something they knew has been replaced. CERN becomes the perfect suspect because its real work already involves ideas that sound strange to non-scientists. It is underground, it uses magnets, detectors, cryogenics, and particle beams. It studies fields that cannot be seen directly. It produces particles that vanish almost immediately and must be identified through traces. It works through decay paths, collision points, antimatter, dark matter searches, and forces that shape the behavior of matter. These are scientific concepts, but they also provide the language for a modern myth about reality having hidden machinery. The 2026 shutdown gives the story a current reason to return to CERN. Long Shutdown 3 is a planned upgrade, not an emergency stop. The machine is being prepared for the High Luminosity Large Hadron Collider, which should allow scientists to collect far more collision data and study rare processes with more precision. In basic terms, this is a practical engineering step, but inside the timeline theory, the shutdown becomes a possible test period. If the collider has been increasing timeline instability, then the shutdown might reduce new glitches. If the collider has been stabilizing one dominant timeline, then the shutdown might loosen that stability. If the most noticeable effects happen when the system settles after years of activity, then the shutdown might be when old fragments become easier to notice. Those three versions give the folklore different paths. In the first version, the running collider acts like a throttle. More collisions mean more measurement pressure, and more measurement pressure means more chances for small timeline overlaps. In the second version, the running collider acts like an anchor. Its constant measurement helps hold one version of reality in place, and when it goes quiet, nearby possibilities drift closer. In the third version, the collider acts like a disturbance whose effects show up afterward. The machine runs, pressure builds, and then the shutdown allows reality to settle, bringing small fragments to the surface, as it does. None of these versions has proof behind it. The point is not that CERN has been shown to move timelines. The point is that if someone wanted to build the strongest possible speculative case, the case would have to involve information, measurement, selection, and memory rather than brute force. It would have to explain why the alleged changes are small, why they often appear in culture, and why they leave behind memories rather than physical evidence that could be tested in a laboratory. This is where shared culture becomes useful, because the Mandela Effect often attaches itself to widely recognized details that many people encounter and repeat. Television, music, advertising, and film all create common reference points that are reinforced over time. When those details are remembered differently by large groups of people, the mismatch becomes more noticeable and more difficult to dismiss as a simple individual error. These kinds of discrepancies tend to exist at a specific scale. They are not large enough to prove anything on their own, but they are familiar enough to feel personal. A line that sounds slightly off, a detail that seems misplaced, or a version of something that feels more correct than the official record can create a sense of unease. The more often a person has encountered that detail, the stronger the reaction can be when it does not match what they remember. There is a more realistic interpretation that may be just as interesting. CERN may not have shifted reality at all. It may have become famous at the same time people were becoming more aware of how unstable memory and information can feel. The Large Hadron Collider began operating in the age of YouTube, online archives, social media, searchable databases, and comment sections where people could compare old memories instantly. At the same time, people were living through financial shocks, political instability, climate anxiety, pandemic disruption, artificial intelligence, and a sense that the future was changing faster than the past could explain. In that setting, the Mandela Effect becomes more than a list of memory mistakes. It becomes a way to talk about disorientation. A person says that a logo changed, but underneath that claim may be a larger feeling that the world itself no longer matches the version they remember. CERN becomes useful as a symbol because it gives that feeling a location. Instead of saying that memory, culture, technology, and time all feel unstable, people can point to the underground machine and say that something happened there. That does not make the theory true, but it does explain why the theory has survived. Every era finds machines to explain its fears. Earlier generations worried about early photographic techniques that people believed could capture ghosts or spirits, radio waves, nuclear tests, satellites, secret laboratories, and government experiments. Our era has particle colliders, artificial intelligence, quantum computing, and the internet. We build machines that change daily life, and then we wonder whether they changed more than we intended. CERN is especially powerful as a symbol because the real science is already remarkable. Scientists there are asking what matter is made of, how particles interact, why particles have mass, and whether the standard model is complete. The Large Hadron Collider did not need folklore to be astonishing. The factual version is already dramatic enough. Thousands of people built an underground accelerator to recreate conditions that reveal how nature behaves on the smallest scales we can test. For this story to stay compelling, it has to avoid overstating the evidence. If we claim that CERN caused every strange memory, the idea becomes easy to dismiss. The stronger approach is to keep the official science in place and then ask what kind of speculation could survive beside it. If timeline shifts were possible at all, they would probably not come from raw collision energy. They would have to come through an unknown relationship between measurement, information, quantum events, and large-scale reality. Present science does not necessarily support that claim, but science fiction and modern folklore can use it as a roadmap. In that imagined version, CERN is not a machine that smashes time open. It is a machine that repeatedly records the outcomes of extreme subatomic events. If reality has adjacent possible versions, and if measurement plays some role in selecting which version becomes recorded experience, then perhaps a machine like the Large Hadron Collider could become a place where neighboring possibilities briefly touch. Most of what happens would remain far too small to notice. Once in a while, the theory says, something recognizable might cross over as a memory. A lyric, a logo, a television line, a remembered death, or another small cultural detail that belongs to one version of the story but appears in the minds of people living in another. That is the unsettling part of the idea. The theoretical changes are subtle because the proposed mechanism is subtle. Reality would not announce the crossing. It would smooth the seam, preserve the official record, and leave human memory as the place where the mismatch remains. If the official story is the whole story, then this is one of the great scientific projects of our time continuing its normal progress. The Large Hadron Collider helped confirm the Higgs boson, and its upgraded version may help scientists study rare processes, test the standard model more deeply, and search for signs of physics beyond what is currently known. That version is clear, factual, and extraordinary without adding anything supernatural. If the folklore is circling something real, then the shutdown becomes the pause before the next phase of measurement pressure. The machine people blamed for time has stopped operating for now, and believers can watch for patterns. Do new glitches slow down while the collider is off? Do old glitches become more noticeable? Does the world feel more stable, or does it feel as if the anchor has loosened? There may be no answer because the theory depends on memory, and memory is not a clean instrument. But CERN remains one of the strongest modern symbols for the fear that reality has hidden seams. Its history is real. Its machines are real. Its discoveries are real. The timeline theory is unproven, but it attaches itself to a real place, a real machine, and a real scientific effort to study the deepest structure of matter. That is why the story belongs here. CERN reaches backward into post-war Europe through the invention of the web, through the first operation of the Large Hadron Collider in 2008, through the Higgs announcement in 2012, and into the 2026 shutdown before the high luminosity era. It also reaches into the more fragile archive of human memory, where old songs, television lines, product names, celebrity deaths, and childhood details sometimes refuse to match the record. Maybe CERN did not break time. Maybe memory is simply less reliable than it feels. Maybe the internet made ordinary memory errors visible at a scale that earlier generations never experienced. But the more unsettling possibility is that small mismatches are exactly what a soft timeline overlap would look like. Not proof, not a new universe, not a complete replacement of the world, but a few details carried across the border between possibilities. The machine under Geneva may have never moved us from one timeline to another. It may only have given us a way to imagine that such a thing could happen. Still, the question remains difficult to shake once it appears. If reality has seams, and if enough pressure is placed on the smallest parts of it, what would slipping through actually look like? It might look like a song lyric that will not sit still in memory, a television line that people remember more clearly than the recording, a logo that seems almost right but not quite, or a past event that feels as if it belongs to two versions of history at once. Thanks for listening to Buried by Time. Remember, time doesn't kill history, it buries it. And if you're drawn to the story still waiting underneath, subscribe to Buried by Time and like the episode wherever that option appears. You can also support the show at buymeacoffee.com/whythankyou. And if there's a forgotten story you think belongs here, leave it in the comments. Until next time, keep looking closely. The past has a way of leaving things behind.